as we've seen with a few other concepts, a graphical representation can be useful to show some quantities related to certain phenomena. And the force time graph is another one that is relevant for momentum. So if we consider the equation that we just saw previously to do with Newton's second law in terms of momentum, we've got F being equal to the change in momentum over time. So that means that we could represent what's going on here using a force time graph. So if we think about a force time graph, we'll have force on the vertical axis and time on the horizontal axis. And usually what we're considering, what we've considered up to this point in time, is that the force being applied is fairly constant. Now, if you consider the area under a force versus time graph, that's going to show us something useful, as it does in the case for a lot of graphs. And basically, again, if we're thinking about an area, that's going to give us the product of force and time, and so that gives us the impulse. So if you think about it, we're multiplying force by the time delta t, and so that's going to give us the impulse of that scenario where force is being applied. So if we say, look at this point here, or this time, then this area underneath that force versus time graph represents the quantity of delta p, or the impulse. Now that's a pretty simplified situation, having a constant force. In reality, the force is often not constant. So many situations involve a force that isn't applied at a constant value. And we'll have a look at one fairly simple case and then one not so simple. And in any situation, it always just comes back to that idea of calculating the area under the curve. So one that's probably a little bit of a simplified scenario, this one. If we look at, again, the force on the vertical axis and time on the horizontal, we might have something where the force increases and then decreases again. So this value here is going to be some maximum force that has been applied, so we'll call that F max. And we've got the time on the horizontal axis. But in this scenario, we still have a case of finding the area under the curve. So there's no sort of hard and fast equation here, but if we think about the change of momentum, or the impulse in this case, it's now going to be the area under the curve. The area of that is, well, the shape there that we're dealing with is a triangle. So we need to find half times the base multiplied by the height. So the perpendicular height here is that maximum force, F max. And the time that we're dealing with would still be delta t, so the time over which that force has been applied. And again, that's going to give us this area under the curve, which is delta p, or the impulse. So that's a fairly straightforward example. In some situations, like we could set up a force sensor with a pass car colliding with it where the spring is extended, and we'll see that the shape is sort of triangular, but not quite. So in that situation, it might get a little bit more challenging. We might need to approximate it as a triangle. But in other situations, it's even sort of worse again, in that we won't necessarily have a very neat output of the force. It might do something that's a little bit more like this, where it's a little bit more random in nature. And so, again though, in this case, we still need to find the area under the curve. So in this case, where there's no mathematical relationship being evident, between the force and time, what we can do instead, the area can be approximated in a different way. And the way that I'm going to state it here is just sort of a rough and ready term. It can be approximated by counting the grid squares. So if we had this on a grid, you could then just go through and sort of count up the number of squares that are covered there. Alternatively, in this case, so let me just note again that ultimately by counting the grid squares we're still just finding that change in momentum or the impulse represented by the area under the curve. For this scenario, if that was the shape that we were dealing with, we could possibly just sort of simplify it a little and treat this first area as a bit of a triangle, the second one as a bit of a rectangle, another triangle through here. So ultimately we're just sort of making an approximation for the shapes that we can see there. So it's not necessarily going to give us exactly the right amount, but it'll give us a good approximation. So there are a number of different ways that you could do it, so by counting the grid squares or approximating areas, but in the end it's always about calculating the area under the curve. So I'll just make that last note, or approximating shapes. So useful representation there, force versus time graphs. The area under those graphs gives us the impulse or the change in momentum of the scenario.